Here we are. Welcome. I'll kick off now. Here we have the plan for today. There's Etienne and myself in a V plant quite recently. We'll talk about what's specific about process industries and V plants, and then apply the 5 focusing steps one by one, and conclude and get on with questions and answers. I'm Philip Marris. I'm the CEO and founder of Marris Consulting. I'm English, but we're based in Paris, France. Historically, I started my operational excellence journey with Lean, as we call it today, in 1984, a long time ago. I've also been implementing a theory of constraint from a couple of years later when I started working with Eliyahu Goldratt, the founder of the theory of constraint. So my world has been mixing essentially those two things and other things into solutions for all kinds of industries. Over 405 right now companies throughout the world, and founded Marris Consulting 20 years ago. This is close to my heart today as a subject because if I know a particular kind of business better than others, it is V plants. My first job is there in that factory in the north of France, making stainless steel, steel seamless pipes. My first flat or house is down there in that picture, so it brings back fond memories. And anyway, I started in a process industry and I went on a bit later designing what is the logo of Marris Consulting in another V plant. So it's close to my heart because I don't know, they're different environments, aren't they? Especially when you have, a lot of molten steel and all these sorts of big cathedral-like factories. I find them particularly exciting and interesting. Regrettably, V plants or process industries seem to have been ignored by many elements of operational excellence. MRP, material requirements planning, therefore ERPs, were not designed with V plants in mind. Lean is always telling you about one-piece flow and all these sorts of things, and then pull flow and stuff, which, as we will discuss, is not always easy to implement. Although these industries are often some of the oldest industries in the world, they've been ignored by modern practices and most posts. So we're going to have some fun here.
Hello, everybody. So my name is Etienne. I will present with Philip today. So I've been working with Marris Consulting over the last 10 years. We do not just work with process industries. We also work with discrete manufacturing. I've had projects about maintenance, repair, and overhaul of aircrafts. So many different topics, but I've learned quite a lot working with chemical factories around the world. So that's why we wanted to share with Philip what we've done and what we've learned about process industries and what we call V plants. So today will be about how to apply the 5 focusing steps in this kind of environments. We've been doing that with many different companies, as I said, in France, but also in many different countries in Europe and even more exotic places. We've gathered a few case studies that we want to talk about. So here you have a sample of our clients, not only process industries, but many different types. But today, we want to talk about process industries and V plants. Maybe, Philip, you want to comment this slide, but the first thing, as I said, we work with process industries, but also with classic assembly lines where lean manufacturing really started. We work a lot with job shops and companies that deal with projects. So here it's one way to summarize the different kinds of industries. There are the high volume ones, the high volume, mid volume, and low volume ones. And there are the ones that deal with low variety of products and the ones that deal with a high variety of products. On this matrix, you can see the different types. And usually the challenge when you are high volume is to increase the flexibility of the line to really stick to customer demands. And that's one of the things that we will discuss today, which is how to increase the flexibility of these process industries that usually deal with very high volume.
V plants are part of the VAT model of the theory of constraints, or sometimes also called VAT and I. These letters are to show what the flow of product is. Watch out, it's special in the sense that the flow goes from upwards, that's to say raw materials or components are at the bottom and finished goods are at the top. So we're talking about V plants, we'll go into detail that, where there are a few different raw materials compared to a very large range of finished goods. Okay, A plants, assembly lines are the opposite, lots of components with a very limited range of finished goods. And T plants are a modern evolution of the assembly line where you try and compensate for having a limited product range by using options and variances of components to produce a wide range of products, and hence the T shape. Typically a car assembly lines, for instance, that sort of product. V-plants, few raw materials compared to a large range of finished goods. That would be in the metal industries, foundries, plastics, chemicals, glass production, paper production, printing, textiles, food, pharmaceuticals, and many, many other domains. Okay, often it's not the case, for instance, of semiconductors and stuff, which are V plants. Often these industries are some of the oldest, right? In class manufacturing, for instance, that sort of stuff. Some of the oldest in the world. So they have this heritage, which can become a handicap. They were ignored by IBM when IBM invented bills of materials and routings and stuff, because you don't assemble things, or not much assembly goes on in a V plant. It's the opposite. You deconstruct, you decompose stuff, right, as it goes through the process. One type of raw material will be transformed into many different types of finished goods. So it's a disassembly process, or if you wish. And so that's a real problem. The culture has been mostly to maintain low cost per unit and not reactive to customer demands. And we will often find low on-time delivery performance. That's a big problem, which we will talk about. The resources lack intrinsically flexibility. We'll talk about things like heat treatment ovens, right? You can think of all the magic you want, but to take it from 500 to 600 degrees is not going to happen in a flash. So there's an issue there. And finding the bottleneck is usually fairly easy in these environments. Please don't try and solve all your problems at once. Stay focused on one particular problem. Choose your fights and focus on those to get your wins, right? We see too many organizations that are unfocused, trying to do a lot of different things at the same time, right? Once you've decided what to do, there are 5 focusing steps, which I'll present very quickly. Have a look at the videos we have that discuss this in further details. Number 1, you find your constraint. Number 2, you exploit it. That's to say, you go immediately to this constraint and make sure and treat it as a VIP resource better than the others, and you should be able to get a lot more performance out of it when you do that. Subordinate to the constraint. That's to make sure that every decision is taken according to that constraint, and in particular, that means learning to avoid local optimums and learn to stop working. Step 4, elevate the constraint. That's to say, get even more out of it by eventually investing or hiring people or whatever. Keep going until eventually the bottleneck moves. Beware of inertia, and then off we go back into this continuous process of improvement. For those who haven't looked at the video, we have specifically all about finding constraints. It's said that, watch out, people do tend to get it wrong. And there'll be an example coming. They confuse where it should be and where it is, and that sort of stuff. It's more and more often in support functions, for instance, in quality departments. We're finding that more and more. Watch out, the identification of constraints can be a problem.
Yes, exactly. So, Philippe, you showed the V of a V plant. What we do usually in process industries is first to make sure that we distinguish the situation for the different lines. You may have some lines that are heavily overloaded with real structural bottlenecks, while others have a lot of extra capacity. So the situation can be very different from one branch of a V to the other. The other thing is that you may have some common resources between these branches, as Philippe mentioned, for example, the quality department. And usually the quality department is not monitored the same way as the other resources in the ERP. So it's usually more difficult to look at the queues of work that they have. You don't have just one constraint for the whole factory, except if it's one of these common resources like quality control, but there's also, why not, quality assurance more and more in pharmaceuticals or in industries like food and beverages, where you have to document everything that you do. Then if we look for these bottlenecks, in process industries, we usually find a few common points that they have from one factory to the other. We usually see that they're missynchronized with the market because of the changeover constraints that they have, which force these companies to run big batches, big campaigns to save time on changeovers. They can be hidden, especially here I'm thinking about the chemical industry, because when you enter these kind of factories, you just see pipes and vessels. So it can be difficult to pinpoint where the bottlenecks are in the process. You don't see the queues of work the same way, but they usually have instrumentation to manage these pieces of equipment, and then looking at the data, you can pinpoint these bottlenecks. So they are often machine driven. So here we usually talk about these big machines in process industries. It's different from other factories where the manpower could be the bottleneck. It's not easy to add additional shifts because they are usually fully open because they are very capitalistic industries. So they run 24/7. And sometimes what we see is that these bottlenecks are blocked for really bad reasons. For example, when the warehouses are full, you are forced to stop the lines. I will not explain all the details, but just to see that from factories to factories, we see over and over approximately the same situations. But it's always important to distinguish the different lines and situations. And when you deal with big factories, this can get complicated because of all the lines that run in parallel. Another challenge in V factories is that you can steal the raw materials or you can steal the semi-finished goods from one resource to the other. So again, we will talk about it, but the synchronization is important. First example, maybe, Philippe.
This is a large steel factory with nearly 3,000 people. This one here is in Belgium. They wanted to apply the theory of constraints, so they said, here's the bottleneck, and they showed us their most expensive, beautiful, impressive-looking machine, their rolling mill, right? And so they said, this is the bottleneck, and this is what we're going to do. So they were wrong. They were confusing where it should be and where it was, okay? In practice, when we looked at the process, it turned out to be the very boring heat treatment ovens that were the constraint of the system, not the rolling mill. They were confusing where the heart of their business was, the most complicated part, the most honorable part, and where the capacity constraint was. So watch out. Very often people are looking at the complexity of their business in terms of what they do, right here, the rolling mill, but it's not necessarily where the capacity constraint is. The second example is another steel plant, 40 meters long by 4 meters wide. That's a huge factory, right? You drive around and stuff. They had a downturn in their market, and the plant was basically underloaded, not working every shift or 5 days a week. So normally they had excess capacity everywhere, and yet they had a problem of on-time delivery performance. So they call me and say, we can't work it out. We have excess capacity everywhere, and yet we can't deliver on time. What's the problem? So we had a look. It was a bit difficult to find this one because normally you look for the biggest queue of one particular spot. And here it was spread in many different areas because the constraint was quality control. And I mentioned it earlier, that's why I took the second example with quality. It's so often the case today. About half our implementations or analysis of industry these days leads to the fact that quality is a capacity constraint, a bad capacity constraint. It should not be. You should have to get rid of that constraint by doing whatever is necessary because it's very bad performance in general. It was the people who walked around the factory with these things that looked a bit like metal detectors, checking the surface of these sheets of metal to see if they were okay. These 16 people out of 2,200 were constraints holding up this huge, very expensive, very capital-intensive factory. So it's completely crazy. Okay, so watch out. Quite often we find hiding in quality, not necessarily the control of the machines, but the paperwork, also the management of quality. Finally, this case here, it's just we worried about including it because people are going to say this is stupid. It's happened to us several times, so that's why we thought we had to say it, right? Quite often, it depends from one industry to another. The finished goods can take up quite a bit of volume, and the factory can produce quite a lot of cubic meters and tons per hour, per day, per week and stuff. So quite regularly, we find that the finished goods warehouse ends up being full, okay? And when it gets completely full, they have to stop the factory. This obviously sounds pretty stupid, but if we're mentioning it here, watch out. We've seen this a bit too often. So obviously, people's focus on productivity and local optimums and stuff is pushing people to this crazy situation where they have to stop production because there's nowhere to put the stuff that they're producing anymore. Next, Etienne.
We just mentioned this case where some of the lines had the capacity to run faster than market demand. And so they were building inventory and they were filling the warehouse with materials that were not necessary in the short term to satisfy the market demand. Doing so, they were blocking the other lines. That's why it's sometimes really tricky to focus locally on the OEE of these different lines without considering the overall situation. When we work with process companies, process industries, they usually use the OEE as a KPI. And in fact, the OEE is made of three components to assess whether the equipment have good availability, good performance, or good quality. But the problem of this aggregate, the OEE is just a number, is that we usually have to get back to the different components of the OEE to really understand the situation. And we don't want to apply it blindly on each and every line without first making a distinction between whether or not the lines have an internal bottleneck or not. Do they have extra capacity compared to the market demand or not? We don't want just to increase OEE without consideration for the demand, customers' demand. And then we want to really understand whether it's a problem of availability or really important quality, or, for example, minor stoppages and performance. Just one word about the minor stoppages, because we've worked with companies where they were ignoring these minor stoppages, but in fact, they accounted for between 20% and 30% of the losses. That was really big. So you may have that, for example, on machines like bagging machines or some of the machines that deal with discrete parts of your processes. If they stop very frequently, but for a few seconds, they may reduce significantly the capacity of the machines. So it's not just about downtime, it's also about these performance and quality topics. Please don't use OEE everywhere, even when there's enough capacity. Then when we talk about exploiting better the bottlenecks, in process industries, one of the main components, the main items is the changeover duration that can be challenged thanks to tools like SMED, but also scheduling. If you look at the changeover matrices where you list the changeover durations from one product to the other, you can find that some sequences are much better than the others. So what we like to do is to work with the teams to see if there's a better sequence, a better order from product to product in order to minimize the changeover durations when it makes sense. For very complex matrices, you may need more sophisticated algorithms, but usually it's sufficient to list the main parameters and to see how to sort them to identify the best order. Be aware that it can be very powerful. And then there is the reduction of the changeovers thanks to SMED. SMED means single minute exchange of dies. It's well known in industrial companies. We usually find that in process industries, it can be improved a lot. What we usually do is we create Gantt charts of the activities. We go into the details of the different activities and we segregate the tasks that can be done before or after the changeover from the ones that must really remain during the changeover, and then we optimize it. So with a Gantt chart, taking into account both the logical dependencies, but also the resources, you can improve it really a lot, usually without investment. But in process industries, because it's a lot about Capex, you can go the extra mile with extra investment. We will talk about it. Regarding the scheduling of these factories, there's one technique that enables to level the load, but also improve the sequence of products, which is called the product wheel. This is usually well known, for example, in the paint industry, where you prefer to go from light to dark, but you have the same in other chemical industries or even in the iron and metal industries. So the idea is to create a fixed sequence of products and to define a cycle. So how often you will produce each product. You're not forced to produce every product within one wheel, within one cycle. You can decide, for example, to produce some products once every second or third cycle. We've created a simulator, which is usually very useful to understand the situation of the line and the impact of the changeovers on the load versus capacity, the impact of sizing this cycle, different cycles, different periods between two products. Understand also when you should produce each and every products on these lines so that you level the load on the line. So this is very useful also to see if you have a constraint or not on one line, to see if just changing a few parameters you can get back to a better situation and satisfy the market demand better. When we talk about exploiting bottlenecks, there's another topic that is usually not addressed, which is finance and throughput. So how many euros or dollars do you generate per bottleneck hour? So that's where it really makes sense to cross operational data with financial data to be able to identify the products that generate the most cash flows compared to the others. Basically, we look at the variable margin and we compare it with the rate at the machine to be able to compare the different products and to see if you have gold mines within your product portfolios. So this was about the how to exploit better the bottlenecks. These are just a few ideas, but in the theory of constraints, we talk a lot about subordinating to this constraint. You can have internal bottlenecks, so resources that can't cope with the market demand, but sometimes you have just a market constraint. You have enough capacity, and the challenge is to stick to the market demand and to deliver on time, really satisfying customers with a good on time in full is usually underestimated because of all these difficult constraints, changeovers, campaigns that you have. And the theory of constraints is a lot about getting back to satisfying the customer demands and increasing the OTIF. The usual way to do that is to implement a drum buffer rope. But before that, you must distinguish whether or not you must produce to stock or make to order, or if you have to do something in between, what we call finish to order. So one of the first steps is to do an ABC XYZ analysis to understand really the patterns of your demand, to see if you have very repetitive products, if you have sporadic demand, and you don't manage these two kinds of demands the same way. Distinguishing between made to stock and made to order is really critical to be able to satisfy the customers and deliver on time. That's where OEE also can be tricky when you want to subordinate to this demand or to subordinate to your capacity constraints, because depending on whether or not you have extra capacity, chasing high OEE can have really bad consequences. We mentioned one, for example, blocking other lines because of a warehouse that is full, but also because if you just want to increase OEE, one way to do that is to reduce the number of changeovers and to increase the size of the campaigns. But doing so, you lose a lot of flexibility. This is also one frequent cause of delivering late. If the line has a lot of capacity, the theory of constraints will say don't optimize locally, take advantage of it and just do more changeovers if you have the capacity to do so to stick to customers' demand. We also usually have to discuss the economic order quantities. When you study it and when you look at the details of how it is calculated and how the curve of the total cost looks like, you will see that in fact EOQ is just a range. It's not a precise number, and you can produce 20% below or even 30% below without having a big impact on the costs. It's important to mention that this model is not perfect. It does not take into account all the costs of holding inventory. It doesn't take into account well the problems of expiry, of insurance, of planning noise generated of seeing the quality problems too late. So really the holding costs are usually drastically underestimated, and it doesn't take into account the opportunity cost. You can take it into account if you want in the formula, but usually it's not taken into account. So again, it's not a sacred cow, and it must be challenged when it forces to produce too big a campaign. The last step or almost the last step of the 5 focusing steps is to elevate the constraint. And that's where we talk about really hard investments, a lot of money. That's where we talk about, for example, installing new pieces of equipment or doing things that take a bit of time. That's why we wanted to mention this topic. It's not really SMED, but it's transitions from one product to another. We categorize it as elevating the constraint because it takes time, because you need to validate the new product, you need to market it. Imagine, for example, that you switch from a peach yogurt to a berries fruits. You have 2 different products, and what you can do is take advantage of the transition to create a multi-fruit yogurt. So this is something that is common in the food and beverage industry, but you can have it also in the chemical industry. Now, that's something that we've done with another company to create a new product and market it. And then, as I said, you can go the extra mile with your SMED approach and add, for example, new instrumentation or modify a bit the machines. So that's where we talk about Capex projects. The theory of constraints has a very powerful way to manage projects, for example, Capex projects. That's something that we've been doing with many industrial companies. At the moment, I think we're helping companies run 4 different big Capex projects. We do that with the critical chain approach. We will do a specific webinar on that topic, but just to let you know that it's a different way to plan and then execute these projects. And one well-known KPI from critical chain is the fever chart. So you have some samples here. So this was a Capex project in a mine to install new equipment. This was a Capex project in a pharmaceutical company where they had to install new machines. You see here how the project went. The theory of constraints is not just about bottlenecks. It's also about finance. It's about project management. It's about strategy and tactics.
It's hard to summarize so quickly, and we're probably going to do another webinar specifically on this subject. It's when you don't have enough work, and therefore some people say, the constraint is in the market. There's excess capacity in all your resources. This happens a lot, at least in European industries at the moment. That's why we're working a lot in process industries for a number of reasons. We said it's that these industries are, for historical reasons, often not client-oriented enough. So often we start by fixing the OTIF, right? They have an OTIF, a terrible OTIF of 30% or whatever. They're losing clients because of that. And so you need to get back to getting good performance. And we did a webinar on that subject, right? It's important with regards to V-plants because they often need to improve the performance of the quality of their offering, not just the quality of the product, but the quality of their offering. Shorter lead times, much better on time delivery. Therefore, you need to look at what's wrong. There might be some bottlenecks or some problems in the sales process, and what your offering is not good enough because the OTIF is not good enough for the reasons Etienne has already mentioned. Local optimums, too much inventory. You need to target particular markets. And again, Etienne's given a couple of examples, okay? Until you created an internal bottleneck, which is what you really want to do, because after all, it's been said several times, we're talking about capitalistic industries, okay? And having a capitalistic industry that's only running 50% of the time is not going to be a good way for making money, is it? Very often, the work is done internally to try and increase the demand from the market on that particular factory. And what we usually do, if you're interested in what we've been saying, is to do a diagnostic of the factory. If it's one factory, one site with less than 500 people, we can usually do that in 2 days. At the end of the second day, given our experience, we can present a diagnostic of the strengths and weaknesses of the organization and a roadmap to improve. Okay, we have a pretty good reputation on doing that. Have a look at all the video testimonials by our clients about us doing this. We do about 1 a week or three a month of his feedback is really excellent. The diagnostic leads to an action plan. That action plan can be developed either by the client without us or with our assistance. It can be some pilot lines, and we work on things such as process order management, not just what we've been discussing here. Okay, that's it. As I say, have a look at all our videos. For those who don't know, there are 600 videos on our Marris Consultancy website and YouTube channel. Okay, I hope you enjoyed this. Thank you very much. Bye-bye.
Thank you very much. Goodbye.